How do we distinguish between strong and weak solutions of acids and bases? Well, a strong acid or base is going to have a higher electrical conductivity for equal molar solutions. And here you have to remember that we are going to be comparing equal molar solutions. Okay, that's the starting molarity of a solution. So say for a 1 molar solution of hydrochloric versus say acetic, the hydrochloric is going to have a higher electrical conductivity. I don't know why I have trouble with that. Rates of the equation. Strong acids and bases are going to have a faster rate because they are already fully ionized. Okay, pH, again, comparing equal molar solutions, the pH for a strong is going to be, for a strong acid, the pH will be lower. For a strong base, the pH will be higher, more basic. Again, because of that fully ionized or dissociated versus the partially for the weaker acids and bases. So how do we determine dissociation constants and calculation, and how do we calculate, say, the pH of a weak acid solution? The generalized acid dissociation equation is this. You need to know how to construct this equation for any acid that you're given. This is the general formula for an acid. You have the hydronium H+, and then the anion. Water sets up an equilibrium with the anion from the acid and the hydronium ion. The Kc, which is more typically written as Ka, hydronium times the anion over the concentration, the original concentration of the acid, is the expression for the acid dissociation constant Ka. Water is not included in this expression because it is a liquid. Give you an idea for what some of the Kas are for different acids and the equations for those. You can look at that table and refer back to it for Kas. So how do we calculate a Ka from the pH? This is where you have to know how to decipher the given information. The initial concentration of your COOH is equal to the molarity given, 0.10 molar in this case. This pH is the hydronium concentration at equilibrium. Okay, so calculating Ka for this, it's a simple matter of constructing an ice table. If we find the concentration of the hydronium concentrate, or the hydronium ion, by doing 10 to the negative pH, I get that concentration as 0.00417 molarity. Setting up the equation, oh geez, I don't know why that's there. There's my equation, ice table. Initially, I know I have 0.1 here. Water does not enter into the equation. At the very start, you assume that I have not dissociated. At the end, I know that my equilibrium concentration here is 417. Since the stoichiometry says that the same change for the hydronium is going to happen for my anion, the stoichiometry change here is minus x. So I would get 0.0958. And 583. Okay. Going up here, the expression for Ka is the concentration of the hydronium ion times the concentration of the methanoate ion over methanoic acid. That's 0.00417 squared over the concentration 0.09583. Doing the math, I should come up with 1.8 times 10 to the negative fourth as my Ka. Calculating the percent ionization. This is another equation that you should know. Percent ionization is the hydronium ion at equilibrium, that's related to the pH, over the initial concentration of the acid. So if we look at the percent ionization of the previous example, my hydronium concentration was 0.0042 over 0.0958 times 100%, and I should get, oh, no, that's not right, no, 0.10. You have to do the initial, not equilibrium, the initial. Sorry about that. That gives you 4.2%, okay? Remember, the initial. We'll continue in another screencast with an example of calculating the pH from Ka.